Well, hey folks, this is Dr. Duncan, your instructor for Biology 101 Explorations in Biology. And today we're going to be talking about our Unit 5 topic, which is climate and biodiversity. This is my first uh, screencast recording of me giving a lecture, so it's going to be awkward at times. I apologize in advance. All right, so let's get rolling. Remember, our question for the course is why Alabama has so many species. Today we're going to talk about one of those four reasons, which is Alabama's warm and wet climate and why we have that warm and wet climate. The other three reasons are referred to in earlier lectures that we've presented. I also want to add that this PowerPoint is posted on your Moodle site, so if you need to look at it just as a just as a PowerPoint instead of looking at it as this video, you have that as an option. Okay, the biosphere is that thin layer on the Earth where all the living organisms are found. And within that, climate is one of the most important factors, if not the most important factor for influencing the distribution of different types of ecosystems. And today we're going to explore how that happens and why that happens. To get there, though, we need to understand four physical processes. These are processes that are that by and large are intuitive and you're probably already familiar with. And one of the things I like about it is that if you understand these processes, you can understand weather and climate patterns wherever you go around the world. So let's start off with the fact that warm air likes to rise and cold air likes to sink. This is driven by changes in air pressure as a parcel of air is heated up and those air molecules want more elbow room, so to speak, and they spread out, and then they wind up rising because the air surrounding them are very dense. You don't have to know all that. Really what you need to focus in on is that warm air rises and cold air likes to sink. This is familiar to you from times when you've been around a fire, like a campfire, or held your hand over a candle and feel that warm air rising, or in the summer when you're barefoot and you open the fridge door and all that cold air floods out and you can feel that on your feet. Okay, the second principle is that due to changes in air pressure, warm air tends to rise as it cools, and similarly, cool air likes to warm as it sinks. And what happens is really as cold air is going from a high elevation to a lower elevation, it will warm because the Earth's gravitational force is pulling those molecules together into that parcel there has more and more density to the air molecules, so they get squeezed together close to the Earth's surface. And when gas molecules get squeezed together really tightly, they bump into each other a lot, and that's what we call heat. So air will warm up as it sinks, and it will also cool as it rises. And that's our second physical process. To help you illustrate this in your mind, to think about this, you can envision how mountaintops are often snow-capped, ice-capped, and they're at higher elevations than the surrounding lowlands, which tend to be warmer. Okay, a third physical process has to do with water vapor, which is water in the form of a gas. And it turns out that warm air can hold a lot more water vapor in it than can cold air. And this is why when you're outside on a cold winter's day, when you exhale, you see your breath. Well, what's really going on there is that in your lungs, in your lung linings, water vapor or water is evaporating into the space within your lung, and then as you exhale, that water vapor is going out your mouth into the surrounding atmosphere. And if it's really cold, what will happen is that those water droplets slow down. I'm sorry, not those droplets, but those water molecules will slow down as they hit those colder temperatures, and they start bumping into one another and sticking together, forming little droplets. And it's those little droplets that you see that's that fog in front of your face in the winter. You don't see the same thing in the summer, and that's because during the summer it's warmer outside, and the air can absorb that water vapor no problem without the water vapor turning into droplets, which of course is liquid form. Our final and fourth physical property is that land and air change temperature much faster than water. Think of water as being very lazy. It is very slow to warm up and very slow to cool down. That old saying, a watched pot never boils, is kind of based on this sluggishness of water to change temperature. Another way to think about this is that during spring break, you might go down to the beach and you hop in the Gulf of Mexico, and it might be nice and toasty warm on the beach, but you hit that water and that water's cold. Well, that's because the Gulf is very slow to absorb heat, and the air and the land next to it have certainly warmed up, but not the water. So these four principles are all we need to understand climate patterns around the planet. So we need to start scaling up and looking at global climate patterns. And to begin to understand that, we need to go back to 7th grade science and take a look at the Earth and its orbit around the Sun. Some basics are things I'm sure you already know, that Earth spins on its axis once per day. Its axis is represented in this cartoon as that solid line that comes out of the top of the Earth and also comes through the South Pole and the bottom of the Earth. And the Earth makes one rotation about its axis each day. That's what we define as a day. And the other thing about this cartoon that you notice is that the Earth's axis is tilted, causing seasonality. Now, the tilt is aligned in the same direction out into space all year long. And that means that during part of the year, when the Earth is, when the northern hemisphere is angled towards the sun, that's when the northern hemisphere gets its summer. During the other half of the year, when the axis of the Earth is pointed away from the sun, the southern hemisphere is angled towards the sun and gets more light than the northern hemisphere. And that's why here we are in February, and we are closing in on the end of winter, whereas in Australia they're closing in on the end of summer. And if you're watching this at other times of the year, you can do that same kind of reversal of the seasons according to hemisphere, and it works pretty well. Okay, so this helps explain why we have seasons on the planet. Now, one of the things that is interesting about this kind of basic planetary science is that all areas on the planet get the same number of hours of sunlight all across the year. And that can be counterintuitive. You might expect that the equator, which is a lot hotter, gets more hours of sunlight than, say, either position on the poles, where we know during much of the year is in darkness. Well, what happens is that the poles get the same number of hours, but they get them all at once. And that's why you can go up into northern Alaska and Canada during the summer, and you've got 24 hours of daylight each day for many, many weeks. So they skip the nights during that time period, and they make up for lost time. Whereas the equator gets roughly 12 hours of sunlight and 12 hours of darkness each day all year long. This differential in the pattern of numbers of hours of sunlight help explain why the poles are colder, because they have a long period during which they cool down, as opposed to the equator getting heated up every day. That's only part of the reason. The other part of the reason is shown here in this cartoon, and that is that sunlight tends to be more intense striking around the equator as compared to sunlight striking near either of the poles. And the reason being is that near the poles, the angle of the Earth's surface relative to the incoming sunlight is more oblique. And so those land surfaces do not get as much intensity of sunlight than compared to the equator. Another way to think about it is that the same amount of sunlight is spread over a small area next to the equator, or at the equator, and is spread over a much larger area closer to the poles. And it's somewhere in between for places like Alabama. This is a major reason for why the equator is warm and the poles are cold, because of that difference in the intensity of incoming sunlight. Okay, so everything we've talked about so far helps explain why we get different temperature zones on the planet. And there's a lot more variation than you see in this cartoon, but this illustrates what enough for us to work with here. And you see that a small portion of the Earth's surface is the polar zone, and that's of course where it's very cold. Then you have the middle belt around the equator that's called the tropic zone, and then the region that's in between that's neither too cold nor too hot, the Goldilocks zone, if you will, is the temperate zone. And that's of course where Alabama is located. And all of this is driven by those patterns that we saw before about the incoming solar radiation and its distribution across the planet. Okay, these temperature zones, with the differences between them, lead to differences in air circulation patterns across the planet, and that's what we're going to look at in just a few minutes. Okay, so what about Alabama? Well, if you look at a latitudinal variation in Alabama, you see that areas to the south are a lot warmer than areas to the north. This is a map of average annual temperature in degrees Fahrenheit. And it might not seem like a lot. We're looking at above between 68 and 70 degrees in South Alabama and below 60 degrees in North Alabama. The differential there is about 10 degrees Fahrenheit, which actually is a lot when you're talking about the average temperature for an area. That means that we've got species living in the north of the state that can't tolerate the hot conditions that are in the south part of the state, and vice versa with regard to the cold that's in the north. The reason that lower Alabama is warmer is because not only it's closer to the equator, but it's closer to the ocean, something that we'll talk about in a few minutes. The ocean, of course, being the Gulf of Mexico. And overall, these differences in temperature variation have a lot of impact on ecosystems in the state. I'll end here and say that this concludes part 1 of Unit 5's presentation on climates and biomes.